Welcome back, students. At the very end of the last lecture, I mentioned that the ideal dilute solution model only applies to non-electrolyte solutions. That is, the solution must not be made up of an ionic compound that will dissociate in the solvent. It will probably come as no surprise to you that solutions containing ions behave very differently from solutions that have no ions. Today, we will investigate these solutions and come up with a model to describe them. The learning goals for today are going to be to first explain why electrolyte solutions are different from the neutral solutions we discussed in the last chapter. We'll then talk about how we can determine the enthalpy, entropy, and Gibbs free energy for these solutions and why we have to use what are called conventional values for these. We'll then calculate the activity coefficients using the Debye-Huckel limiting law, which is a law that allows us to come up with a theoretical model for dilute electrolyte solutions. And finally, we'll calculate the equilibrium constant and use that to do things like actually determine experimentally the activity coefficients for ionic compounds. Let's start by considering the two reactions shown below. We have gaseous hydrogen and chlorine molecules dissociating into gaseous hydrogen and chlorine ions, or aqueous hydrogen and chlorine ions. Are these reactions favorable? Are these reactions favorable? Our chemical instincts tell us that hydrogen and chlorine will not likely dissociate in the gas phase, but these ions, H plus and CO minus, are favorable in solution, suggesting that it will dissociate in solution. This means that aqueous H plus and CO minus must be lower in free energy than gaseous H plus and CO minus. Why is this the case? We're already familiar with the reason. Ions make favorable interactions with polar solvents such as water that stabilize their formation, and these interactions are not available in the gas phase. We want to start by trying to identify the energetics of these processes. There is a challenge that comes up because we can never isolate a single ion. We can't have a solution of only H plus or CO minus. There's always another ion that comes in solution. So if we have a solution of H plus, we have to have CO minus, or maybe we have nitrate or hydroxide or something. We can't just have H plus in solution. So we can't really experimentally measure and isolate just the ionization of a single ion. What we do then is set the free energy, entropy, and enthalpy change of one ion, namely aqueous H plus, to 0. So you can see that here, that aqueous H plus is set as 0. When we do this, we can come up with say an enthalpy of reaction. So we can talk about the enthalpy of this reaction. The enthalpy of this reaction is, of course, equal to the enthalpy of the products minus the enthalpy of the reactants. Here, hydrogen and chlorine molecules are gases in their most stable state, so their enthalpies are 0. We define H plus as 0, so the only one of these that actually has an enthalpy is aqueous chlorine. And so there, when we do that, the enthalpy measured in this process is simply the enthalpy of formation of chlorine. And you can see that listed here. So when you dissolve HCl, you end up with negative 167.2 kilojoules of energy, and that's measured as the enthalpy. We can get the Gibbs free energy from measuring the equilibrium constant, and we can measure the equilibrium constant because if we have ions in solution, we can measure the electrical conductivity of that solution, which tells us how many ions there are, and then we can go back out from there the amount of those ions and get an equilibrium constant and use that to get a Gibbs free energy. And then if we know the enthalpy and the Gibbs free energy, we can calculate the molar entropy as well. I want to point out here that some of these molar entropies are negative. Now, this might be a little bit disturbing because entropy is always positive, but we have to remember that these aren't true enthalpies, or Gibbs free energies. They're all relative to hydrogen ions being 0. So with that in mind, we can note that say that copper 2 plus having entropy of negative 99.6 joules per Kelvin per mole doesn't mean that it's less entropy than normal. What it means is less entropy than a hydrogen ion. And so for this reason, since these are all scaled relative to hydrogen, we call these conventional enthalpies, conventional Gibbs free energies, and conventional molar entropies because they're defined by the convention that the hydrogen value for all of these is equal to 0. And this is very much like what we do for setting hydrogen and chlorine equal to 0, just having some standard state. We just have some reference because it doesn't really matter the absolute values, only the differences between them when we're doing these problems. Once we know that H plus is 0, we can calculate Cl minus. We get this here. And then if we did something like, say, dissolve sodium, we would have sodium plus ions and chlorine minus ions, and we can calculate out from the heat that's released what the enthalpy of just sodium is, and then we can do that for every other ion that exists. We next want to consider if we can describe the solvation of ions. So we have an example reaction here that is an H plus gaseous ion becoming an H plus aqueous ion. To figure out the energetics of the solvation here, we first determine how much work it would take to remove an electron from an atom in the gas phase, and do the same thing then for the solution phase. This is a form of electrical work, so we use Coulomb's law. We integrate to determine the amount of work it would take to convert a neutral sphere of radius r to one of charge q. So using Coulomb's law, the work is equal to the integral of charge times the change in charge over 4 pi epsilon naught, which is the permittivity of free space, times the size of the sphere r. And we're integrating from no charge to a charge of q. So integrating this gives us q squared, and then we have a 1/2 q squared, so it'll be 8 pi epsilon naught r. If we did the same thing in solution, everything would be the same, except for the permittivity would be different. So the permittivity of a vacuum is this constant epsilon naught. In a solution, it's epsilon naught times epsilon r, where epsilon r is the dielectric constant of the solution. So this is for the free ion or the gas phase. And then in solution, we would have q squared over 8 pi epsilon naught epsilon r times r would be our solution work. So the energy, the Gibbs free energy, is related to the work. So we can say that the delta G of solvation here, going from the gas, the free ion, to this aqueous solvent, is equal to the Gibbs free energy for the aqueous phase minus the Gibbs free energy for the gas phase. And what we'll do to convert between the work and the molar Gibbs free energy is simply multiply by 1 mole. So this will give us q squared times Avogadro's number over 8 pi epsilon naught epsilon r times r minus q squared times Avogadro's number over 8 pi epsilon naught r. And then we'll substitute in what q is, what the charge is. The charge is simply the z, which is the number of charge, it's 1, 2, 3, whatever it is, times e, the fundamental charge here. And so when we do that, we get z squared e squared times Avogadro's number over 8 pi epsilon naught r. And then I'll factor out the remaining term, which is 1 over epsilon r minus 1. And this is an equation that we can use to approximate the delta G of solvation. So looking at this plot here, we can see that our model doesn't actually do a very good job at predicting the experimental data. So the dashed line is the model and the dots are the experimental data. And maybe for these smaller ions, it's okay, but for the rest of these down here, it's pretty bad. What we can recognize is that the R we're using here is the size of the ion, and that's not actually the best R to use, because if we were to drop an ion in solution, it's not free in solution, it actually is interacting with water molecules around it. So instead of using the actual radius of the ion, if we use the effective radius, which is the center of the ion to the center of the water molecules surrounding the ion, we can come up with a model that much better represents the experimental data. So our line here is much closer to the experimental data. And with this in mind, we think it might be possible to come back and evaluate this Hess's law setup here. So we have these first two equations, which talk about the dissociation of hydrogen and chlorine, which we can know. We know the bond energies. We can talk about the ionizations of hydrogen and chlorine, which we can also know because we know the electron affinities and so forth. And then the last part is the solvation. So if we have this model for solvation, maybe we can apply that here and sum these all up and get the total delta G naught reaction for this process. Now, this doesn't work. And the reason for this is that there's generally a pretty large error. And you can see the delta G solvation energies are on the order of thousands of kilojoules per mole. And so for something like a lanthanum here, we're off by a little bit. And that might not be so bad. It looks pretty good. But when you try to plug that into something like Hess's law, we already know how that works. So these generally give errors on the order of 50 kilojoules per mole. And if the total answer is negative 130, that 50 is going to totally screw us up. So in general, we don't pursue this kind of strategy and instead rely on the conventional values that we saw on the last slide. We cannot apply the ideal dilute solution model to even very dilute solutions of electrolytes. Why not? Because the positive and negative charges interact with each other in an electrolyte solution. Electrostatic interactions are in general very long range, meaning we have to account for them. And if we don't, our model is going to be horribly wrong and miss the energetics of these electrolyte solutions. So we're now going to seek to describe the Gibbs free energy of an electrolyte solution. We'll start with this equation shown here. The Gibbs free energy of an electrolyte solution is, of course, equal to the moles of solvent times the chemical potential of the solvent plus the moles of solute times the chemical potential of the solute. With an electrolyte solution, our solute breaks up. So we can actually break up the solute part of this equation and say that the Gibbs free energy is equal to the moles of solvent times the chemical potential of the solvent. But then for the solute, we can say, well, there's a certain number of plus ions and a chemical potential of the positive ionic species. And then there's a certain number of moles of minus ions and the chemical potential of the minus ion species. And we could also write this in a slightly different way where we pool those together. So the number of moles of positive ion is simply the total number of moles of solute times the stoichiometric coefficient of the positive ion. And the same is true for the minus ion. So we could also write it in this fashion if we chose. And we have this expression now that the chemical potential of the solute here is simply equal to this here. So a chemical potential for the solute for an ionic solution is equal to the stoichiometric coefficient of the positive ion plus the chemical potential of the positive ion plus the chemical potential of the negative ion, and then the stoichiometric coefficient of the negative ion. Now, we have an issue, and the issue is that we can't actually measure these values. We come into the same problem that we had before. These things are always linked, and so they're not independent of each other. So instead, what we do is define what's called a mean ionic chemical potential. And we'll give that the symbol of chemical potential and then plus minus because it's the chemical potential on average for both of these ions. And this is simply the chemical potential of the solute divided by nu, which is the sum of the stoichiometric coefficients there. And then this equals nu plus mu minus over nu. We can also describe the mean ionic chemical potential based on the mean ionic activity. And we've seen an equation like this before. We can have mu plus minus is equal to some standard mean ionic chemical potential plus RT natural log of the activity. And again, we have a mean ionic activity. We define the mean ionic activity usually in the following way, where we raise it to the nu, again, where nu is the sum of the stoichiometric coefficients. And it's equal to the activity of the plus ion to the plus, and then the minus ion to the minus here. We then define the activity of ions based on their molality. Like before, we have the activity is equal to the molality multiplied by an activity coefficient. So the activity of the plus ion is simply equal to the molality of the plus ion over a standard molality, that's 1 molal, times a gamma, which is our activity coefficient, and we have the same for the minus ion. So this is our definition here of activity. And remember, the activity coefficient is best thought of as some sort of correction factor. So we could have a 1 molal solution, but it acts like a 0.8 molal solution, and then the activity coefficient is 0.8. We're not quite acting like we're at the concentration that we are. We then substitute these expressions in to determine the mean activity coefficient based on the molality. So we can substitute in this here and this here, and that will give us that the mean activity coefficient raised to the nu is simply equal to the plus molality over the standard molality raised to the nu plus, the same for the minus. And then we have gamma to the nu plus and gamma to the nu minus. If we add these things together, we simply end up with gamma to the nu. And we can also do the same thing with the molality. So we can have m plus minus over m naught raised to the nu times gamma plus minus to the nu. And so here, gamma plus minus is simply this, and m plus minus is equal to that here. So we can say that m plus minus raised to the nu is equal to m plus to the nu plus, m minus to the nu minus, and then the same thing for gamma. And so we have all these definitions here. Now, I know this is kind of confusing, and there's a lot of things going on here. We're going to boil it all down into one equation that's not necessarily pretty, but hopefully is a little bit more easy to understand. So with this in mind, we can define the chemical potential of our ionic solution. So our chemical potential of the solute, going all the way back up here, is equal to nu times the mean ionic chemical potential. And we know what the mean ionic chemical potential is based off of activity, and we know what the activity is, so we'll go through this one step at a time. So this gives us nu times a standard mean ionic chemical potential plus nu, well, I'll put it this way, plus RT natural log of A plus minus raised to the nu. We know that A plus minus raised to the nu can be rewritten in terms of molality. So we'll go ahead and do that. This will give us mu plus minus standard times nu, and then plus RT natural log, and I'll put these in brackets here. We'll have m plus minus over m naught raised to the nu times gamma plus minus raised to the nu. And then we'll break up our m plus minus. And so with this, right, what is the m plus minus? Well, we know that m plus minus here can be rewritten as m plus times m minus. What's m plus? M plus is the molality of the positive ion. If we have a 1-to-1 ion, right, the molality of the positive ion is the same as the molality of the negative ion, which is both equal to the overall molality. If we have a 2-to-1 relationship, say something like a calcium hydroxide or something, then our negative ion molality would actually be twice as high, which is the stoichiometric coefficient here. So we can also say that m plus, right? We can say that m plus is simply equal to nu plus times the actual molality, and m minus is nu minus times the actual molality. And so putting these things together, we can have a little bit of a different expression that's just based off the overall molality of the solute and not necessarily considering the ions. And that would be nu plus raised to the nu plus, nu minus raised to the nu minus, and then we just end up with the molality raised to the nu there. And so with this, we can substitute that in and end up with the following. We have nu times chemical potential, so for the standard state, plus RT natural log of nu plus raised to the nu plus, nu minus raised to the nu minus, and then we'll have the molality of the solute itself over the standard molality raised to the nu, and then we still have our gamma plus minus raised to the nu. And so what we'll do here is break this apart into 4 terms. So we'll say the chemical potential of the solute is equal to nu times a standard chemical potential plus RT natural log of nu plus raised to the nu plus, nu minus raised to the nu minus, plus nu RT natural log of m over m naught, plus nu RT natural log of gamma plus minus. So what do we have here? We have 4 terms in this equation. We have this first term that can be thought of as a normal Henry's law standard state. So this term is one that's saying, well, if everything was normal, right, and wasn't an electrolyte solution, we had some concentration of something, this is what the chemical potential would be at 1 molar of this solute. The second term here alters it by the formula of the electrolyte. So a 1-to-1 electrolyte would be different than a 2-to-1 or a 3-to-1 or a 3-to-2 or anything like that. So the concentration of the electrolyte, how the electrolyte breaks up, changes the standard state. And what we can do if we so want is we can pool these 2 terms, and it's sometimes done, as this constant here that talks about like an ideal electrolyte solution. These last 2 terms we're actually more familiar with. So this term here talks about deviations with respect to different concentrations. So here we're assuming we have a 1 mole solution in these first 2 terms, and we don't actually have a 1 mole solution. We have to correct based on this third term here. And this last term is a correction based on the activity coefficient. So we're not ideal. We don't act like we have the concentration we do. We have to change that based on our activity coefficient, and we have that term here. So these 4 terms can explain what we have with our ionic solution. The activity coefficient can be determined experimentally by doing things like measuring the freezing point depression and boiling point elevation, other colligative properties, but it is often determined using electrochemistry. We'll see in the next bit here that we can also calculate the activity coefficient relatively reliably using electrostatic theory. Why can we model electrostatic solutions? Well, it turns out that when you have ions interacting in solutions, they're interacting more or less like ions. And that allows us to treat them more or less like ions and ignore the kind of solvent-solute interactions that were very important previously, because we can say, well, these ions are going to interact like ions. So the Coulombic interactions are dominating over the normal interactions, and we can use what's called the Debye-Huckel model to estimate how these guys are interacting. In solution, every ion gives off an electrical potential, and the electrical potential symbol we use is a phi. In dilute solutions, the interaction between another charge and the electrical potential will be much lower than the available thermal energy. This allows us to use Coulomb's law to determine the electrical potential of the ions in solution. Here, simply using Coulomb's law, we can determine the electrical potential of an isolated ion. That is the charge of the ion, so that is Z for the number of charge, and then EP. I'm using the P here because we have the number E over here to separate them out. So this E sub P is the fundamental charge of the electron and the proton. So the amount of charge, if we have a +2 ion, it would be 2E, and so forth. Now that ion exerts its charge based on Coulomb's law, so we have 4 pi epsilon naught times the dielectric constant of the medium times the distance. In a solution, however, with not just a single ion, we have this other term over here, E, this is the number E, raised to the minus kappa R. So what we're saying with this term is that the electrical potential falls off faster in an actual solution than if we had an isolated ion. And this is due to screening of other ions in solution. So if there's other ions present, those are going to mitigate the electrical field that one ion can then emit, because it's going to kind of cancel it out after a certain point. We can describe this constant, and Debye-Huckel theory does so. They describe this kappa constant as the following. So we have E, the fundamental charge of the electron squared, times Avogadro's number. We have a conversion to convert from having the density in liters to cubic meters for SI units. We have the molality. We have the charges of the ions here, and then we have our constants. You can note the way I've colored these things that we have different properties coming from different places. So in blue, we have what are just fundamental constants. We have conversions, we have permittivity of free space, Boltzmann's constant, temperature, and so on. In green, we have solvent-dependent constants. So the permittivity of the solvent and the density of the solvent. And then in black, we have solute-dependent constants. So depending on what we want to do, we can actually pool a lot of these together. So we can say that kappa is equal to 2.91 times 10 to the 8th times I, where I here is the ionic strength. And the ionic strength is defined down here. And then we can plug that in for this m times these guys here. And then we only have these, the ionic strength, which is the solute dependent, and then the density and the permittivity, which are the solvent dependent. And then if we want to apply this to water, which we often will be talking about aqueous solutions, we can plug in the density and the mean and the permittivity of the solvent for water to get 3.29 times 10 to the 9th times the square root of the ionic strength. And here we can see the Debye-Huckel model and how it predicts how the charges fall off. And we can see that the charges fall off pretty rapidly for high concentrations as compared to low concentrations, reflecting that there are more ions packed together for these high concentration solutions. With this in mind, we can use Debye-Huckel theory to formulate the Debye-Huckel limiting law, which describes the mean ionic activity coefficient based on that constant kappa. So we have the natural log of our activity coefficient is equal to negative z plus times z minus, the values of the charges there, times the proton squared here, times kappa over 8 pi epsilon r kbt. And these are all constants except for kappa, which depends on I. So we can plug in all the constants to get that the natural log of gamma plus minus is equal to negative 1.173 times the magnitude of the charges times the square root of the ionic strength. And this is sometimes also reported as a log base 10. So this is it down here reported as a log base 10. So how does this law stack up? Let's consider. For something like silver nitrate, singly charged ions, it works pretty good for a lot of values of ionic strength, maybe up until about 0.2, 0.3. For something like calcium chloride, it works for small values, but it starts to fail a little bit sooner. And if we look at a sort of a larger scale here, we can see that it's pretty bad overall for large values of ionic strength. So for this reason, we call this a limiting law because it works under limiting situations, namely dilute electrolytes. There's a lot of reasons why it fails for high concentrations of electrolytes, and some of those include not accounting for the finite volume of ions and assuming that they're point charges, and then also not considering that the solvent is actually molecules that interact with the ion as well. But the point is that this model works for low concentrations and not for high concentrations. We can attempt to fix this with the Davies equation. The Davies equation is in the book. I don't have it here. What the Davies equation is essentially an attempt to fix the model using empirical data. So it's not grounded in theory anymore, but it kind of has the same shape as you would expect. So it's more like a real gas law, like the van der Waals equation and so forth, and less grounded in theory than the Debye-Huckel model. We can also apply everything we've done here to determine equilibrium. So we can determine the equilibrium coefficient just like we've done before. The equilibrium coefficient is equal to the product of all of the activities raised to their stoichiometric coefficient. And we can define the activity based off of the concentration. And we can do this and then figure out what's happening for chemical reactions. Now, since the Debye-Huckel law, it only works for dilute concentrations, this is best applied to things with very dilute concentrations of solute, such as scarcely soluble salts. So we can do an example like the dissociation of magnesium fluoride into magnesium and fluoride ions. The equilibrium constant, we define that as a KSP. You remember doing these before. But now we can think of the KSP based not simply on the concentration like maybe we did in Gen Chem, but on the activity. So the equilibrium constant is equal to the activity of the magnesium ions times the activity of the fluoride ions squared. And since the activity is based on the concentration times the activity coefficient, we can come up with this equation here. And there's a relationship between the concentration of the magnesium ions and the concentration of the fluoride ions. So with this, we can come up with two equations. We can say that the concentration of magnesium is equal to X, some amount of dissolved magnesium, and the concentration of fluorine would be twice that, it would be 2X. And then we have our activity coefficient here. So we have X times 2X squared, so 4X cubed, times the activity coefficient we don't know cubed is equal to the KSP. Again, the KSP can be measured experimentally through things like conductivity. And so with this, we have one equation and two unknowns, and you might think that we're stuck and we can't solve this. But what we can actually do is use an iterative approach for this that's represented here. So we can start by assuming an activity coefficient of 1, and then we would have 4x cubed is equal to this number here, and we can pretty easily solve that. So we divide by 4 and take the cubed root, and that predicts that the concentration of the magnesium is equal to, say, 1.170 millimolar. And then we can multiply that by 2 to get the concentration of fluoride ion. Now, with those concentrations in mind, we can go to our Debye-Huckel limiting law and calculate the activity coefficient based on the charges of those and the ionic strength. And we can calculate that because we know the molality and we know the charges there. So then we can get an estimation for what the activity coefficient is, and that is 0.87. And then we can redo that first calculation using our new activity coefficient to get a new concentration and repeat until we don't change anymore. This is an iterative approach. And so after 3 or 4 cycles, you can see we're pretty much stopped here with a gamma of 0.860904 and a concentration of about 1.359 millimolar. So assuming an activity coefficient of 1 actually gets us an error of a few hundredths of a millimolar. And here's another example done for calcium sulfate, which needs much more iteration before it finally sits on a good value there. And this is a pretty much bigger error because the activity coefficient is much lower. So assuming 1 gets us a concentration of about 2 millimolar, and the actual answer is about 4. So we're off by a factor of 2 without using this iterative approach. That's all that we have to say for electrolyte solutions. So remember that electrolyte solutions are differing from neutral solutions, mainly because they have ionic interactions. But this actually allows us to formulate the Debye-Huckel model and the Debye-Huckel limiting law, which allows us to have some equations actually grounded in theory that describe these things. We rely on conventional enthalpies, Gibbs free energies, and molar entropies because the ions are always coupled, and the conventional values give us more reliable measurements than these experimentally or theoretically determined values. And we can also solve for the activity coefficients and actual concentrations of these scarcely soluble salts using an iterative approach like we just did. In the next couple of lectures, we're going to keep talking about electrolyte solutions, but we're actually going to go into electrochemistry and learn about transitions of electrons and so forth, and go into how those things work.